Welcome to Almost Sure. Now, if you've watched my previous videos, you might notice some changes going on here. If you haven't watched my previous videos, then why not? I'll wait. Okay, yeah, my office is gone. It's replaced by this beautiful bird here. My big microphone is gone, and I'm actually standing up today. There is a reason for these changes, and that reason is that I was recently invited to give a colloquium talk in the beautiful and historic city of, well, yes, Vienna. And if this talk had been recorded, then I'd just have posted it here. But it wasn't recorded. So I'm redoing it especially for YouTube. And I'm going to reuse the same basic slides from the original talk. And in fact, this image here of Vienna is one that I took from the venue, just straight after the talk. So this is authentic. And no fancy on-screen graphics today. If I have anything to add, which isn't on the slides, then I've got a blackboard. Now, this talk was on martingale theory and an area which has many applications in finance, and I published some papers on this a few years ago which had some results in there which I'm pretty proud of. I'll go into those later, and has some interesting and consequences. So yeah, that's what I'm going to discuss. That's what I did discuss in the talk. Anyway, let's bring back the slides. Martingales and the Peacock Problem, let's go. Now, as this talk is all about martingales, let's just start with the definition of what a martingale is. Now, if you're not already familiar with these, then this might be a little bit confusing, but I do have a couple of videos already on this channel about martingales, and it's recommended you check those out first, and then you'll probably understand this more easily. But let's continue. And the definition here, well, let's have a look at a couple of examples first of all. So these are the two basic types of martingales. First of all, in discrete time, we have a random walk, and this is just a process that at each time step, it increases by 1 or it decreases by 1, each with 50% probability. For example, tossing a coin. Let's suppose you're betting $1 on each coin flip. And so you win $1 if it's heads, and you lose $1 if it's tails. And then at any time in the future, then your total winnings at that time follows a random walk. Now that's a discrete time process. But we also have continuous time processes, and probably the most famous of these is Brownian motion. Now, Brownian motion, or mathematical Brownian motion, is, well, it's a continuous process. It is random, and at each time it's just normally distributed, and in fact its increments over each time step are normally distributed and independent of the values at all previous times. So yeah, that's Brownian motion. And then another example, or more general type of martingale, would be these Ito diffusion processes, which are essentially just Brownian motion, but its volatility is scaled by some function of the process itself and time. So that's an example of a stochastic differential equation. So let's just look at this definition. So yeah, just standard stuff. We have a probability space with the sample space omega. We have the sigma algebra F, this curly F, which represents the subsets of the sample space. It's a sigma algebra of these events, and then P is a probability measure on the events. We have our process X, which is indexed by time T, and T could run over the positive integers or non-negative integers for a discrete time process, like we saw with the random walk, or it could run over all the positive real times, as we saw with Brownian motion. And then the next ingredient is this filtration, which is a sequence of sigma algebras, one at each time, representing all information up to that time. Then we say that x is a martingale if it's a expected value. Well, if we take a time s less than time t, and then we take the expected value of the process value at time t, conditional on all information at time s, then we should get the value of the process at time s. So this means that on average it stays the same. There's no sort of bias, or there's no drift, so it's not increasing on average or decreasing. So this is, it's like the fair gambling game. X could represent our winnings at any time. If it's fair, then on average it does not increase or decrease. And then we have technical condition that it's integrable, and also that it's adapted, which just means it's observable at time t. So yeah, hopefully you know a little bit about martingales. This talk is geared towards mathematicians. So let's move on. So let's start with a very basic statement of the problem here. And this is, suppose we have two probability measures, which I'm representing by mu and nu here. And they could be on the real numbers or more generally in d-dimensional space, so on r to the d. And the question is, can we join these by a martingale? That is, can we find a martingale such that at time 0 its distribution is mu, and at time 1 its distribution is nu? Well, I'm only considering martingales here with a single step, so t equals 0 or t is equal to 1. We're not at the moment considering continuous time processes. And this is a kind of, well, it's a coupling problem, which is something that is very useful in probability theory, where you have some random variables or you have some probability measures and you want to combine them on the same space, but sometimes this can be done in a way which is very convenient. We choose their joint distribution to have nice properties. And here the nice property is, let's suppose we set our variables at x and y, then we want the expected value of y conditioned on x to equal x. So that is the martingale constraint. And I've put the keywords here of coupling and also transport. So this is the kind of thing that you see with like transport or optimal transport problems, where we want to move from one distribution to another distribution in some sort of constrained way, and often this is done as optimal transport, where you're trying to optimize something. But here we're just trying to keep the martingale constraint. Now there's obviously constraints on the distribution before you can do this. For example, if x at time 0 is the expected value of x at time 1 conditioned on your information at time 0, then you can just take the expected value of this and see that they must have the same mean. So you can't just do it with any two distributions. And in fact, Strassen in 1965, he found the exact constraint on these probability measures to be able to do this. And that is that they are increasing in the convex order. Now I best explain what the convex order is here. So let's move to the next slide. Suppose that we have a martingale, which is x, and then we have some convex function f. Then if we apply f to our process, then Jensen's inequality says that the expected value of f of x at t is greater than or equal to the expected value of f of x of s when t is greater than s. Now this is pretty straightforward, but it's a necessary constraint here, and it turns out it's not only necessary, it's sufficient. But we will use this constraint to define this ordering on probability measures. So we say one probability measure is less than the other in the convex order if it's the expected value of convex functions are less than the expected value of the same convex functions with the other measure. So yeah, this is a necessary thing to be a martingale, and flipping back to the previous slide, according to Strassen, in his 1965 paper, this is an if and only if condition. So in fact, this is a general thing that happens with coupling often, that there's two ways to characterize properties between measures. One is some property of the individual measures themselves, like the expected values of convex functions, and then the other is in terms of representing them on the same probability space. And that's exactly what we have here. Increasing in the convex order is the same as being able to represent them by this simple 2-time-step martingale. So let's move on to a slight generalization of this problem. Suppose now we have multiple time steps, so we have n of them. So time t can be 0, 1, 2, up to time n. And suppose that we have n probability measures. Now, well, maybe you guessed what the problem is here, and that is, can we find a martingale which has these distributions at each time t from 0 up to n? And the distribution of a process at a fixed time, this is called its marginal distribution. So this is quite a fairly common thing. You might know the distribution of a process at each fixed time, but we want to know the joint distribution. So here we are starting with the distribution at each fixed time, and then we want to know, is there a joint distribution which makes it a martingale? Yes, according to Strassen, yes. If it's increasing in the convex order, then you can fit a martingale. And in fact, this was shown in the same paper as the previous single time step result, and it just follows from that. You just apply Strassen's result across each of the individual time steps and you join them together. And when you do this, the process that you get is Markov. So you get that additional property, just like the future is independent of the past, conditional on the present. So the Markov property, if we have our process with time going along in that direction, we take our process x, it's evolving over time in some way, and then we take 2 times s and t. If we're to take the expected value of some function of x at time t, and we condition that on the information time s, then we get a function of x of s. The statement that this is always a function of x of s is precisely the Markov property. So in this simple case, yes, we get a Markov martingale fitting all our probability measures if and only if they are increasing in the convex order. Okay, so let's step this up and move on. Let's look at continuous time. Suppose we have probability measures now which are defined at every positive time, that is every positive real number time. And I'm representing these by mu of t, and these are probability measures on the real numbers or on r to the d, so d-dimensional processes. So these represent the marginals of a process. Now the question is, if we have all these probability measures, is there a martingale fitting all of these measures? So at each time t, its distribution is equal to mu of t. And the answer, again, is yes, if and only if it's increasing in convex order. And in fact, this follows from Strassen's result again. In fact, he didn't actually prove this as far as I know in his paper, but it does follow from it by taking the limits. You just take your continuous time and you approximate it using a discrete set of time steps, and then you take the limit as this discrete set of times becomes more and more dense in the positive real numbers, and then you can use some compactness ideas and take a limit and you get a martingale fitting all of the marginal distributions. But there is one problem: the Markov property is lost. So the process that you get, it's difficult to say what it looks like. It doesn't have any nice regularity properties. So the question is, can we do better? And in fact, Kellerer showed at least in one dimension, so these are real valued processes, then yes, you can find a Markov martingale fitting these distributions, if and only if they're increasing in the convex order. In fact, he did rather more than that. He showed that they are Lipschitz and strong Markov. Now, Lipschitz Markov, let me show what this means. If we go back to our original statement of the Markov property, that by definition, the expected value of a function of x of t conditioned on events at time s is a function of x of s. Now, suppose that we have f being Lipschitz continuous. So its gradient is bounded by a constant in absolute value. Let's say it's less than or equal to 1. Then the Lipschitz Markov property says that we can take g to also have gradient bounded by 1. This is a nice condition because it's preserved under taking limits. Suppose we have a Markov process and we want to show it is, well, let's suppose we want to generalize the time s to be a random time or a stopping time. We could, for example, take the first time that this process hits 0, and then that could be our time s. The idea is that you could approximate this first time at which it hits 0 here by a time which can only take finitely many values. Let's say the first integer time, or just take some finite set of times and take the first of those after our stopping time, and look at that. So if this was, get rid of that s, I suppose this is our time s, which is now random, we could take some times just after that, and maybe we approximate it. And the Markov property will follow through to these stopping times, which occur at a discrete set of times. But then when we take the limit, you lose the Markov property. That's because when you take the conditional expectation, this function g could be very nasty. It doesn't have to converge to anything. But when you have this Lipschitz constraint, then you're bounding the derivatives of these functions. It will converge to a nice limit. So what that means is that if a process is Lipschitz Markov, then this Markov property generalizes to where s is any stopping time. And then t, well, it could be a stopping time, but it has to be greater than time s. And this is, in fact, is known as the strong Markov property. And normally, when we're looking at Markov processes, we're really interested in the strong Markov property rather than the Markov property. And that's because why do we want to restrict ourselves to these deterministic times? In practice, if we have some time, it's going to be like the time the process hits some value or something like that. So pretty often it's going to be a random time, and we need the strong Markov property. Now, Markov processes don't have to be strong Markov. Let me give you an example of a Markov process which is not strong Markov. So again, we have time going in that direction. Then suppose at time 0, we flip a coin. If the coin comes up heads, then we'll take our process x and just let it stick at 0. If it comes up tails, then let's suppose our process x moves like a Brownian motion, doing whatever it does. So if it's tails, then we get this Brownian motion. Now if we take 2 times s and time t, then at time s, suppose the process is, well, I suppose it's not equal to 0. The only way that could happen is if we got a tail at the beginning, so we know it's evolving like a Brownian motion, so we know its distribution at time t is going to be conditional on x of s. It's going to be some normal distribution with mean x of s. But if it's equal to 0, the probability of our normally distributed random variable at time s, x of s, the probability of that being equal to 0 is 0. So we can't be in the Brownian motion situation. We must be stuck at 0. We must have got a head at the beginning, and then we know that x of t will be 0. So that's a Markov process. It's pretty weird because it has these two states. But what happens if we were to take the first time? Let's suppose we take the first time after some positive time that it hits 0. So then we can see now x of s is there. So now we have x of s is equal to 0. So it really gives us no information. And then we don't know if we're in a situation where we have a Brownian motion that's hit 0 or if we are stuck at 0. So we don't know the distribution of x of t just conditioned on x of s. If we looked at the history of the process, then we would know. But the point of the Markov property is that the future distribution should just depend on x of s. So that's an example, this two-stage process, either Brownian motion or stuck at 0. That's an example of a Markov process which is not strong Markov. And these are not very nice processes, and normally we'd look for the strong Markov property, and that's guaranteed by Kellerer's result. So let's summarize what we have learned so far, and we'll start with a definition just to tidy this up a bit. This set of probability measures, mu of t for each time positive time t, this is called a peacock. And this terminology, well, it's relatively recent. I wasn't aware of it back in 2010 when I wrote some papers on this subject. And I've heard it was coined by Markov. I'm not 100% sure of that. Anyway, it's got nothing to do with a bird. It is an acronym, surprise, surprise. And it's actually an acronym for this French phrase, meaning processes that are increasing in the convex order. Or processus, well, you can see. My French is not great. But anyway, the abbreviation PCOC, just pronouncing it in English, we have peacock. And if I just flip to the next slide, we see here two examples of peacocks. First of all, over here on the left, we have the peacocks we're interested in here. And I plotted the probability distribution of the process evolving over time. This is a martingale process. You see it's becoming more spread out over time. And then we have the bird, which is obviously irrelevant to anything. But if you look at the peacock's tail, even though it's just for an acronym, I kind of think you see it spreading out like that. It's kind of like a process spreading out in the convex order. And in fact, it will look even a bit more like that when I get onto some examples in a moment. So let's go back to the previous slide. So what we have seen so far is that the marginal distributions of a continuous time martingale is a peacock. And this was just something that followed from Jensen's inequality. But we had the opposite direction, that any peacock gives rise to a martingale. Well, not necessarily a unique martingale, but there exists one, as proven by Strassen and Kellerer. But this leaves open some questions. What about more than one dimension? In that case, we know a martingale exists which fits this peacock, but we've got no idea what it looks like, and is it even Markov? And the next question is there a unique martingale fitting the peacock? In general, the answer's got to be no. It's easy enough to come up with different martingales, even Markov martingales. We'll look at some examples in a moment which fit the same peacock. But I mean, what additional properties can we add to make it unique? And what does the resulting martingale look like? Martingale theory and peacocks, although not using the same terminology, has found major applications in finance. For example, suppose we have a tradable asset and its spot price is given by x of t. So every time t, the value of this asset is given by x of t. For example, we can have stocks, we can have bonds, commodities like oil, gas, or precious metals, and so on. Then the idea in option pricing theory is that you have this risk-neutral measure or equivalent martingale measure. And as the name suggests, under such a measure, the price of these tradable assets is a martingale. Okay, if you look at any actual sort of finance paper, then there's various adjustments for interest rates, funding, dividends, etc. But if we ignore those, then we can say it's a martingale. And the idea is that we have a contingent claim, which is a derivative or an option. It has some payoff. For example, a call option gives you the right to purchase some asset, maybe a stock, for a given price called the strike price at a given time in the future. So this has a value which will be the difference between its actual price at that time and the price you can buy it. So if the strike is K, then this will have value x of t minus K. And you would only exercise this option. You have the choice whether to actually purchase the asset at that time. So you're not going to go ahead if it's got negative value. So the actual payoff is the maximum of x of t minus K and 0. So that's the example for just a simple vanilla call option. But you can have more general types of contingent claims, and we want to value them. And in this world where we're ignoring interest rates and so on, then the initial price of such a claim is just its expected value. So we need to know the distribution, or we need to know the joint distribution of x in order to calculate this expected value. So what we have here is exactly the kind of thing we're looking at. We have a process and we want to find its distribution. In fact, it's a martingale. We want to find its distribution in order to be able to price these contingent claims. So moving on. For call options, which I just mentioned, we have this, the price of a call option is the expected value of the x of t minus the strike price, which I've called x here, maxed with a 0. And it's quite a neat thing about these is if you just differentiate twice with respect to x, you get a probability density function. In fact, you kind of look at this in a sort of hand-wavy kind of way. If you differentiate the maximum of x of t minus x with 0, differentiate that with respect to x twice, then you kind of get a delta function about x. So you take the expected value of this delta function is a probability density. So the probability density of x of t is second derivative of call prices. This is a well-known thing in option pricing theory, and that you get these implied probability densities. And this is demonstrated in the next slide here, where I've shown 3 plots. The first one is call prices as a function of the expiry time t and strike price x. And these are, as you can see, convex functions in x, and well, maybe it's not so clear, but it's increasing in time t. And in fact, this increasing in time t, this is equivalent to the Peacock condition that is increasing in the convex order. And then in the second plot, I've taken the second derivative of this with respect to x to show you the probability density. You see it's spreading out. And then I also have the third plot here, which if you're familiar with these kinds of things, then they're often shown in terms of implied volatilities, or these are what we would call a normal implied volatility, where for each call option, you try and back out this volatility, which is an overall scaling factor to the Brownian motion that corresponds to that call option price. But because just the scaled Brownian motion doesn't necessarily fit all of the distributions, then you're going to get a different value of this volatility for each strike and each maturity. So you get this curved surface as shown up there. And the fact it's not constant is equivalent to saying that it can't be fitted with just a Brownian motion, or geometric Brownian motion is often used. Now, this idea that we have all these call options and we can back out the probability distribution at every time for our underlying asset x. This is a starting point to option pricing. So we have all this information. How do we fit a model to this, fit a process to x that is consistent with the information that we have? And this was something that's been solved in a couple of different ways. Derman and Carney, they solved this problem in 1994 by looking at the local volatility model. And in this model, we have a stochastic differential equation, dx equals sigma of x comma t db, where here b is Brownian motion, Sigma is a local volatility surface. It's a function of the level x and time t, and dx is our infinitesimal change in the asset price. And the idea is that this sigma, our volatility surface or local volatility surface, can be fitted to all of these marginal distributions. And the way that Derman and Carney did this is by using the binomial tree approximation. On the left here we have just a regular binomial tree. So this represents the process as a random walk, as we saw earlier. Each time you can either go up or down with 50% probability. And if you make your time steps very small, it approximates a Brownian motion. But then they modify this, they introduce this sigma. This changes the binomial tree a bit, as shown on the right. So you have this kind of deformed binomial tree. And you can do this in such a way to match your distributions, or approximately. This is the approximate method. And around the same time, Dupere, he looked at the local volatility model via a partial differential equation. In fact, it can be shown that your call prices as a function of your expiry time t, strike price x, they satisfied this partial differential equation. And this partial differential equation only involves your call prices, which you know, and your local volatility, sigma of x comma t, which is what we want to find. So we can use this to back out the local volatilities, and that gives you, again, this Ito diffusion with the local volatility surface, which should match, in theory, all of your call option prices. Now this has a lot of conditions, right? Is there a unique solution to this stochastic differential equation? And we have to take a whole load of derivatives. So you have to assume everything is smooth. And then when we do have a solution to this partial differential equation, or in fact to this stochastic differential equation, is it necessary that you get the same call prices back out? There's a lot of assumptions here in terms of uniqueness of existence of solutions to the partial differential equation and to the stochastic differential equation. So there are constraints here. Things should be smooth and so on. And this shows the idea. So the same as before, right? We have our peacock on the left represented by these call prices, which again are convex in the strike price x and increasing in time. Then we can back out a local volatility surface, which is shown on the right there. And indeed, in this case, everything is smooth, and you get back your distributions at each time. This is a well-known idea in the finance industry. So just recapping there, we are modeling our asset by this Ito diffusion, which is the local volatility model. And we back out the local volatility from call prices via this partial differential equation. And then we are guaranteed existence and uniqueness as long as everything is sufficiently nice. But what about more general one-dimensional peacocks? What happens if we don't assume that everything is all nice and smooth? And this is the subject of some papers that I wrote. First one's been published around 2008, though I put a question mark here, and that's because I actually looked at these in the late 90s, around about 99, 98, but then published it later, around 2008. Anyway, this result says that if you have your peacock, you just have to assume it's weakly continuous. That means that in time, your probability distribution is continuous in measure as you go through time. And this is a fairly weak condition. It's much weaker than saying that your underlying process is continuous. And with this condition, then we're guaranteed that not only does there exist a strong Markov martingale fitting the marginals, there's a unique strong Markov martingale which satisfies this additional almost continuous property. The idea is that we want to fit a continuous strong Markov martingale to the marginals, and my results show that if there does exist a continuous strong Markov martingale, it is unique. On existence, there will always exist a continuous strong Markov martingale, with a slight caveat. There's some sets of marginal distributions or some peacocks where this is kind of obvious that it's not possible. I'll just show you how that can happen. Let's suppose that, again, we have time increasing, and then maybe we've got two levels, whatever we want to call them, x and y. And let's suppose that the process has 0 probability of being inside these levels. So it's never inside there. And then we'll have some probability at each time of being less than x and some probability of being greater than y. Now, if the process is continuous, then it could never cross there, because if it passed between x and y, then it would have some finite probability of being found between those levels at some time. So if you have this case where the process can never enter some region, but let's suppose the probability of it being below x, suppose that changed. The probability being less than x, if that's decreased, then that must refer to some probability that the process moves into this region, and it can only do that by jumping. So there are some marginal distributions where there is no continuous process that fits them, whether it's a martingale or Markov or anything. You just can't fit them by a continuous process anyway. And then my result shows that if this is not the case, for example, we can guarantee this is not the case if our marginal distribution, our mu of t, if its support is an interval, maybe it's the whole real line, or it's the positive real numbers, or maybe a finite interval. If the support's always an interval, this never happens, and you're guaranteed to find a continuous strong Markov martingale fitting these marginal distributions, and furthermore, it is unique. In the cases where there is no continuous process fitting the marginal distributions, the idea is that there is a almost continuous process which is as close to being continuous as is possible given this constraint. If we're back in this situation, the process can't enter this region, but the probability of it being less than x, suppose that's decreased over time. So there's some probability of it jumping across. If we say it can only jump across this region there, it doesn't jump any further. That's kind of the almost continuous property. Now this statement, it might seem kind of innocuous at first, but it's actually surprisingly strong. And let me demonstrate this with some examples, and it has some pretty counterintuitive and surprising consequences. Let's go back to our process that we had before. This was the example of a Markov process that's not strong Markov. So we toss a coin. If it's heads, then we just come along. We stay at the origin. If our coin comes up tails, then we move like a Brownian motion. Now this is a martingale. It's not strong Markov, but it is a martingale. So if we take its distribution at each time, call that mu of t, then this distribution is going to look like, well, it's going to look like a normal distribution. So its density is going to look like that at each time, but then it has a delta function at 0 because you've got 50% chance of being stuck at 0. So we have this peacock, which is given by the marginal distributions of this martingale. Therefore, there is a strong Markov process, or strong Markov martingale, which matches all these distributions. And as this probability distribution, its support is the whole of the real numbers, then you don't get into this problem with discontinuity. So there's going to be a continuous strong Markov martingale fitting the distribution. But it can't be your original process. That's not strong Markov. So what is this? What does this process look like? In fact, we can say it's going to look like a Brownian motion when you're away from 0. The question is, what happens when you hit 0? It can't stick there. In fact, you can show that these continuous strong Markov processes can't just stick at a level. So it keeps moving, but every time it's got a positive probability of being at 0, even though it never stays at 0 for any interval. So it moves like a Brownian motion, going up and down, but somehow it manages to stick there for kind of an infinitesimal length of time, or somehow gain a positive probability of being at 0 at every time. So that is one example. Let me give you another example. Suppose we take a process which starts at 0. It stays there until some random time t. T, let's suppose it has a continuous distribution. Let's suppose it's got exponential 1 distribution. So its probability density is like e to the minus t. So this is just a random time. It doesn't matter, it's exponential. I'm just choosing any continuous distribution on the positive reals. And then at time t, let's suppose it just jumps to some other level and sticks there. So it'll come along, it'll jump to some other level and stay there. But this other level has some distribution, which let me call that mu, which is independent of the time. Is this a martingale? Well, yes, if mu has 0 mean, then this will be a martingale. Let's suppose we say mu is just standard normal. So mean 0, variance 1. Process comes along, it jumps to some normally distributed random variable, and then it sticks there. This is a simple martingale with a single jump. So its distribution at each time, it's going to look like, well, its distribution at each time is either at 0 or it's got this normal 0, 1. So its probability density is going to look like a normal, but again with a delta function at 0. So there exists a strong Markov, continuous strong Markov martingale, which fits all of these marginal distributions. But what is it? Well, it can't be the original process that's not continuous. So there's some other continuous process which has this distribution at each time. And it's going to look a little bit like our sticky at 0 Brownian motion that we saw before. But let's take this a step further. Okay, so let's suppose our distribution mu is on the rational numbers rather than being normally distributed. And the rational numbers, as you probably know, are countable, so they can be listed in order. Say Q1, Q2. Let's suppose we list the positive rational numbers in order, and then we assign some probability to each of them in such a way that that sums to a half. And then we can say that it assign the same values or the same probabilities to the negative rational numbers. So you get a symmetric distribution. For example, we have a half, we have a third, 2/3. Well, I suppose we have 1 here somewhere. We have 2, and then so on. List all the rational numbers, and then you assign some probability, like a quarter, an eighth, 16, so on. And we have our process, comes along to time t, then it jumps to this rational number and it sticks there. Again, if you make this symmetric between jumping to the positive and negative rational numbers, it's a martingale. So its marginal distributions give a peacock. And so there must be a continuous strong Markov martingale fitting all these marginal distributions. That's what my result implies. But what does this look like? We know it's continuous because the support of the rational numbers is just the closure, it's the whole real number line. So there's no gaps for it to jump past. So it's going to be a continuous strong Markov martingale. As it's continuous, obviously it has to move through all the irrational values. Between any two rational numbers, there's uncountably many irrational numbers. But at every time t, its distribution is going to be given by this on the rational number line, or it could be at 0, which again is rational. So now we have a continuous strong Markov martingale, which is never constant, it's always moving, but at every time t, it has this distribution, which has probability 1 of being rational. So yeah, it's kind of counterintuitive, but it follows naturally from just considering this result. But how can we prove this? Well, you could look at my papers, but I'll just give a sort of kind of brief idea. First of all, we want to try avoiding using this stochastic differential equation, the Ito stochastic differential equation, which had this local volatility. That's because we're not always guaranteed that such processes can be described by an Ito diffusion. But we'll start off still by considering the local volatility model. But rather than using the stochastic differential equation, we'll use what's called the backwards equation. If we have some function of our process at time t, then we, rather than moving forwards through time diffusing the process, we can move backwards looking at the expected values or conditional expected values of this final value, which in option pricing theory would be like looking at the value. This conditional expected value is like the value of a payoff that you are moving backwards through time in order to get to time zero and calculate the current time zero price. And we can write down the partial differential equation that these conditional expected values satisfy. So if we look at this, I used f of x and time t for this expected value, and in fact satisfies this equation here, which is the backwards equation, also known as the Kolmogorov backwards equation. They're very similar in appearance. In fact, we can combine them in order to cancel out the local volatility sigma. We do that, then we get this nice symmetric looking formula at the bottom. Second derivative of f with respect to x multiplied by dc by dt plus the same thing with f and c exchanged is equal to 0. And now we don't have any local volatility, so maybe this applies more generally. But it still relies on f, our conditional expectations, and c, our core prices, being all nice and smooth in order to take these derivatives. But this problem can be approached by trying to smooth it out. The idea is that we just multiply by some nice smooth test function theta, and then just integrate over space and time in order to smooth out these derivatives. And in fact, by a few applications of integration by parts, we get this identity. The left-hand side was just the formula that we had, which is our backwards equation with local volatility cancelled out. So we have that on the left-hand side, we want it to equal 0. Then using integration by parts, we get this thing on the right-hand side. Still has derivatives in it, but only first-order derivatives. And in fact, we can make sense of this, even if things are not smooth. For example, call prices, they're convex in the strike price x. And it's a mathematical fact that convex functions have derivatives, first-order derivatives, at least one-sided derivatives. So like the absolute value of x, if you look at this as a function, its derivative is +1, or its right-hand derivative at 0 is +1, its left-hand derivative at 0 is -1, so it's not differentiable at 0, but it does have its one-sided derivatives. And we always have things being right-hand, or convex functions always have this right-hand derivative. Yeah, so we can still make sense of our derivatives with respect to x, at least for the core prices. And also, the core prices are increasing in time. That was exactly the convex ordering property. And that means that the derivative with respect to time, even though it might not exist as a pointwise derivative, if you take the derivative of c with respect to time and multiply by dt, this exists in the sense of measures. So the measure theoretic derivative exists. And then you can actually do the same with f, although that's far from obvious. But you can show that f can always be taken to be convex in x and decreasing in time t. And this is actually something that I published although it's based on ideas from an earlier paper from 1998 by Hobson. So eventually we get something which kind of makes sense. Mathematically, we can write down this condition that this double integral of all this stuff here, these derivatives, one-sided derivatives, and measure theoretic derivatives with respect to time. This gives a condition. You can say this should equal 0. But does this really give you a valid condition for these conditional expectations to hold? If it did, that would give you the full distribution. And you can show it does. It is very difficult to show, but it does result in a valid equation for saying whether f is in fact equal to these conditional expected values. From that you can imply that there is a unique strong Markov martingale continuous or almost continuous matching the marginal distributions. Existence of them is another question, but that can be done by taking limits. It's a bit simpler, and you can show that there always exists these almost continuous strong Markov martingales. So after going through all this, you get, yes, there is a unique almost continuous diffusion martingale which matches your peacock. We can go further than this though, and it can be shown that the map from these peacocks or these call prices to the measure or the martingale measure, the almost continuous diffusion martingale measure, this itself is continuous in that a small change to the call prices or to the marginal distributions leads to a small change in your resulting martingale measure. Not only is it continuous, but it's the unique such continuous map. So we don't even need to mention almost continuous diffusions or the strong Markov property. There is a unique continuous map from these continuous peacocks to martingale measures which are consistent with a peacock. And it happens that unique continuous map is this one that maps it to the almost continuous diffusions, your strong Markov almost continuous martingales. Again, that's in one of the papers that I published back around 2008, although it's based on stuff that I worked on in my thesis back around 1998 or 99. Now let me show you another way that we can use this result that I proved to generate some fairly weird and wacky martingales. Now let's do a cunning trick here. Let's suppose we take normal distribution, often represented by gamma. And if we multiply this by or scale it by square root of t, we have gamma of t. That's normal distribution would mean 0 and variance t. Now we know that this is a peacock and unique continuous, almost continuous strong Markov martingale fitting it is just standard Brownian motion. But what happens if we restrict this to a set? So I'm going to take a set A. And we're going to look at normal distribution conditioned on it being in A. Then, as long as A is symmetric about 0, then it will still be a symmetric distribution with mean 0. So if we take, we take gamma of t restricted to square root of t times A, because we've scaled everything up by square root of t. So we have our process, right, which looks like this. And at time t, let's call this process y. Its distribution is going to be just normal restricted to set A. So A was a couple of intervals, then was multiplied by square root of t. So our process is actually going to be restricted to being in that. So take square root of t times A would be like this region, and because we're choosing symmetric sets, we have this region. So we have some process which is going to move along in this region, jumping across maybe. If we have a gap like this, it's going to jump. Okay, so that's process y. But let's introduce another process, which I'll call Z, or Z if you prefer. And this is going to be exactly the same thing, but we're going to take the complements of A. So that's all this region. And we have our process Z, which is restricted to lying in that region, possibly jumping across region A. Now these are two strong Markov martingales, but if we take another process, let's say X, which is equal to Y with some probability, with probability, well, it's going to be gamma of A, because that's just the probability that your normal distribution is in A, and we set it equal to Z with with probability 1 minus that, which is the same as gamma of B. Then we have this process X will just have a normal distribution with variance t at time t and zero mean. But it's not strong Markov. It's Markov, but it's not strong Markov. Now we can generate some weird processes by doing this. This is as shown in the slide here. But the set A, it can be chosen so that its measure on any interval is non-zero, and such that the measure of the complement of A on any interval is non-zero. And this is a slightly weird property. The set A has to be dense, its complement has to be dense in whole real numbers, so it's not something you can just display easily. But such sets do exist. If you do that, then you can show that the processes Y and Z in fact will be continuous, because the support of these marginal distributions is the whole of the real numbers, which, as I mentioned earlier, these almost continuous diffusions, if the support is the whole of the real numbers, then they will be actually continuous. So we have these two continuous processes, continuous strong Markov diffusions and martingales, Y and Z. And then if we take this process X equal to Y with one probability or Z with another probability, this is what we call a fake Brownian motion. It looks very much like a Brownian motion, but it isn't. It has many of the same properties, but not quite. In this case, it doesn't have the strong Markov property. It has continuity, it has the martingale property, it has the Markov property. It just fails the strong Markov property. And this is actually the subject of a paper that I published along with Schachermayer, Palmer and Bielbrock in 2021. And while I'm discussing my result, let me mention an unsolved open problem that came up while I was working out the proofs. And I mean, this is maybe slightly self-indulgent of me here, as I don't know if anyone is really interested in this, but it is a problem that came up, and this was back in 1999, so it's 25 years later. I still don't know the answer. So let me just state this. If we just take a continuous one-dimensional martingale x, and we take some function f of x, of the real number x and time t, and suppose it's convex in x and decreasing in time t, then is f of x and t a semi-martingale? Now, it's almost true. If it was increasing in time t rather than decreasing, the answer is yes. And in fact, you can, by approximating it by smooth functions and using Ito's lemma, you can show that it satisfies this stochastic differential equation. Right? df of x comma t is f primed of x comma t dx plus something which has to be increasing, which means it's a semi-martingale, as a semi-martingale is a martingale or local martingale plus a finite variation process. But if you change that increasing time t to decreasing, it suddenly becomes a much more difficult problem. In fact, you can show all different types of equivalent statements, some not involving stochastic processes. For example, it's equivalent to saying any such function f can be decomposed as the difference of two functions g and h, which are convex in x and increasing in t. The best that I've been able to do here is to show that your f of x and time t is equal to this integral, which is a martingale or local martingale, plus a term which has zero quadratic variation. And to be a semi-martingale, this final term, which has zero quadratic variation, would actually have to have finite variation. Now, like I say, I don't know if this is true or not, but I do have a possible counterexample, and I've put this on my blog. I'll link to it. I'll link to it in the description below, but I haven't been able to show it really is a counterexample. And this is where the function f is very nasty. It has this fractal property. I'm showing it here. It's convex in x. It starts off just being constant in x, and let's say at time t equals 1, it has this shape like a V shape, but then times in between, you kind of partition it and then give it V shapes in the little bits in between to have this kind of fractal description. And then we take a martingale, which has a similar sort of fractal property. It jumps between these levels where the function f is not differentiable. But it's still, well, actually it doesn't jump, it's continuous, so it moves between them. And numerically, it looks like this is not a semi-martingale. Like I say, I have a blog post which goes into this in detail. I kind of hope that the result is not true, in the sense that it doesn't have to be a semi-martingale, and that this is a counterexample, as that would mean a lot of the stuff that I did proving my result was actually required. If this was a semi-martingale, my result, well, if you could show that this is always a semi-martingale, then the results that I proved in my paper would become much easier. Okay, with that out of the way, let's move on to the final, more sort of speculative area of this talk. What happens if we look in more than one dimension? As we saw, then we can always fit a martingale to a given peacock. And in fact, the problem is highly underdetermined. Suppose we just looked at Ito diffusions, which might be appropriate if everything is nice and smooth. In that case, we have a d-dimensional Brownian motion in our stochastic differential equation. So our sigma here, rather than just being a real number value for the local volatility, it's now a matrix. It's a d by d matrix, symmetric matrix. The number of degrees of freedom is, well, it's this d times d plus 1 over 2, which is just the number of degrees of freedom of a symmetric d by d matrix. But the constraint that we have is just a single probability density at every time. So that's like one constraint, and then we have all these degrees of freedom. If d is equal to 1, then we see that this is 1 degree of freedom, so that's why it was plausible that it would work. But once we go up to more dimensions, we're not going to get a unique, nice martingale diffusion fitting the densities. Although there has been some work recently in the multidimensional case, though the results are much weaker than we can get in the one-dimensional case. For example, there's a paper by Palmer, Robinson and Schachermayer in 2024, and they showed that you can always find a strong Markov martingale, in fact an Ito diffusion, fitting a peacock if you regularize it. So you kind of convolve your marginal at each time with that of a Brownian motion marginal. So existence kind of works as long as you do this regularization. However, we don't always get solutions. Like even if you do regularization, but you start off at time t equals 0 without doing regularization and then just regularize at future times, then there are examples in 4 dimensions where there's no strong Markov continuous martingale matching the marginal distributions. Well, that's the 4-dimensional case. I don't know about 2 or 3 dimensions. Maybe there's counterexamples in those cases. Seems likely. We don't get uniqueness. Even if we look at standard Brownian motion in 2 dimensions, there are strong Markov, martingale, Ito diffusions which have the same marginal distributions. That is a 2-dimensional Gaussian at each time, which again, just by considering degrees of freedom, is not surprising. So this leaves many open questions, right? I mean, we know that in multi-dimensions that we don't get uniqueness, and we don't always get existence. So what can be done? I mean, we have to change the question a bit, right? I mean, what additional structure can we impose that would guarantee existence and uniqueness? I mean, I don't know of any. As far as I know, this is just an open problem. And another way of looking at this is using optimal transport. Rather than just trying to find a unique solution, try and find a solution which is close as possible to some nice solution that you have. How could we move from one martingale process to another in an optimal way? That requires some measure of distance. So that gives you a kind of analog to the Wasserstein distance, which some people have looked at. Or another way of looking at this is find a process which mimics this given marginals according to a peacock, but is closest to your desired process in some metric, like stretched Brownian motion. These are kind of very interesting ideas. I think one issue with this theory is that a lot of it is very kind of abstract. If we go back to the results back in the mid-90s from Dupier and from Derman, then these are all about option pricing, and they're very useful results that are still used today in the finance industry. But then you have a lot of more abstract mathematical results. But this idea, I think, of optimal transport, find something that fits the marginal distributions, which is close to a nice process that you would like to use, that could be a practical thing. And people use all kinds of models in finance, like stochastic volatility models. Maybe you could start with a stochastic volatility model and then say, what's the closest thing to a stochastic volatility model that matches your marginal distributions? That kind of thing could be interesting. Anyway, that's just my thoughts on it. And with that, that finishes the talk. For me, I've got a plane to catch. I've got to get back to my office, back to my home, so I can make more videos for you guys almost surely.